All right, so today I'm going to revisit the notion of span, which I started right at the end of last week, but I thought it would maybe be good to just do a little bit more on it. Okay. So first, let's remember what the definition with span was. So we have a vector space V, and then we have some collection of vectors V1, Vk, for some number k. So these are vectors in V. Okay. And we defined the span of the vectors V1 through Vk. This is defined to be the set of all linear combinations of the given vectors V1 through Vk. Okay. And then if we, to say that these vectors span the space V, okay, so that just means that their span is equal to V. But then since the span is all linear combinations of these vectors, then to span the whole space means that every vector in V is a linear combination of V1 through Vk. Okay. And then to write that out, maybe like more mathematically with less words, you could say for every vector, let's see if, oh, let me try to do arrows on the vectors as well. Okay. Okay. All right, so here I'm just going to rewrite what I just stated. So to say that every vector in V is a linear combination of V1 through Vk, that's saying for every vector B in V, there exists scalars C1 through Ck, satisfying C1 times V1 plus dot 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 plus CKVK is equal to B. Okay. All right. Okay. So then let's kind of separate that off. Okay. And I did one example last time, I think, of checking whether 3 vectors and I think R3 happen to span R3 or not. So I thought I'd do maybe just one more example, but this time in a different vector space. So in this example, let's take the vector space of 3 by 3 upper triangular, or let's do maybe 2 by 2. I think that would be shorter. So let's do the space of 2 by 2 upper triangular matrices, which I'm going to denote as U2. Sorry, all upper triangular. Okay. So U2, again, is the vector space of all 2 by 2 upper triangular matrices, and Here I'm going to create some matrices right now. Let's say this first matrix V1 is going to be 1, 0, 0, 1. So the identity matrix. V2 will be negative 3, 2, 0, 1. And let's say V3 is maybe 2, 6, 0, 0. Okay. And we want to check. So right now, notice that all three of these vectors are upper triangular matrices. Okay. So these are vectors in the vector space U2. Okay. All right. And we want to check if these three vectors in the vector space U2, we want to check if these guys are going to span our space. Okay. Okay, so what we need to do then is we want to check this condition over here. So we want to check if every upper triangular 2x2 matrix is a linear combination of the three that we were given. So to check that, I'm just going to start by forming a linear combination. Let's do a scalar times our first vector plus another scalar times our second vector and plus another scalar times our third vector. So we have a linear combination, and we need to check if any 2x2 upper triangular matrix is a combination of these guys. So here, notice that I'm using like arbitrary letters for the entries of this matrix on this side, because we need to check if every 2x2 upper triangular matrix is a combination of the ones that we were given. Okay. All right. All right, now this is going to lead us to a system of equations. So if we kind of multiply and add the first entries on the left, we get 1x minus 3y plus 2z. And so all that would need to be equal to a on the right-hand side. If we look at this second entry, we're going to get 0x plus 2y plus 6z. And all of that would need to be equal to b. Now here, since these are upper triangular matrices, now this entry is going to be 0 for all of them. So you just get 0 equals 0, which isn't really worth writing down. So I'll just look at the last component. So we're going to get 1x plus 1y plus 0z. And that would all need to be equal to c. Okay. So we're led to the system of equations, and what we're trying to do is we're trying to see if there is a solution to the system. Okay. So you check if there's a solution x, y, z. All right, so in order to check that, we're just going to start solving the system of equations. And we'll solve it the way that we usually do, which is doing elimination. So let's maybe start by doing row 3 minus row 1. So if we did that here, we'd get 1 plus 3 is 4. 0 minus 2 is negative 2. C minus A. Okay. And I want to do at least one more operation. So let's say I want to get rid of this 4. So let's do row 3 minus 2, row 2. Okay. Okay. And if we did that, we get over here negative 2 minus 12 is negative 14. And then here we get C minus A minus 2B. Okay. Okay. Now at this point, we've reduced it to the upper triangular form, so we'd now be able to solve this system by doing the back substitution. Yeah. Now for this problem though, it's not important that we find the solution. All we need to do is to check if a solution exists. And here we can see that a solution does exist because we'd be able to solve with back substitution. Okay. So since a solution XYZ always exists, no matter what we have on the right for ABC, that means that these 3 upper triangular matrices do span the space U2, okay? All right. All right, so then let's maybe do one more example. Let me fix that real quick. Okay. So maybe let me do one more example as well. So we just did an example with matrices, but occasionally you do have a few questions involving a space of polynomials. So I thought maybe let's just do one example of those as well. Okay, so this time I'm going to take the vector space P2. So let's remember that P2 represents the space of polynomials. Oh, that's weird. Of degree less than or equal to 2. I don't know why things keep moving around like that. I'm just going to leave it as it is though. Okay. So here we have a different vector space, this time a vector space of polynomials. So let's look at 2 vectors in this space. Let's say vector v1 is going to be the polynomial x squared. X squared plus 2x. Let's create another vector in this space. Okay, let me make sure. Okay, there we go. Right, sorry about that. So just making sure I unmuted myself. So here I was going to look at the vector space of polynomials of degree less than or equal to 2. And so right now I'm just creating 3 vectors in this space. So the vectors are going to be polynomials of degree less than or equal to 2. So I've created one vector, here's another vector. in this space. And then here's maybe a third vector in this space as well. And then we're going to kind of do the same thing. We're going to ask if these three polynomials that we have here, these three, are going to span the space P2, okay? Oops. All right. Okay, so to check if these three are going to span our space, we'll kind of set it up the same way that we did before. So to span the space means that every polynomial in the space is a linear combination of the three that we were given. So what I'll do is I'll form a combination right now of our polynomials. Let me use a C1, C2, and C3 for the scalars this time. So C1 times B1 plus C2 times B2. Okay. And plus C3 times B3. Okay. And here I want to check if any polynomial of degree less than or equal to 2 can be written as a combination of the polynomials that we were given. So here I form a combination. I'm setting it equal to like an arbitrary polynomial of degree less than or equal to 2. Okay. So that's similar to how up here I had to set it equal to an arbitrary 2 by 2 upper triangular matrix. I guess let me try to fix this again. So for some reason, the text keeps shifting up for some reason, but I'll try to fix and see if it holds. Okay. Yes. It is, yes. Yep. I wonder if I can, oh, I can zoom in a bit, right? Whoa. All right, better? Okay, all right, cool. Okay, so let's see how we would handle an example with polynomials. So for polynomials, what we want to do is we want to go ahead and distribute everything out on the left first. Okay. So what I'm going to do is I'm going to distribute everything out and then I'm going to combine like terms. So I want to combine all of the x squared terms together. And after distributing, I want to combine like all the x terms. And I also want to combine all of the constant terms at the end, okay? Okay. All right, so let's say if we were to distribute everything out, we would have a C1 x squared. So I'll put C1 here. We'd also have a 3C2 x squared. And we'd have a 3C3 x squared as well. Okay. So we have, those are all the x squared terms combined. Next, for all the x terms, we have a 2C1x plus 5C2x, okay, and then plus 4C3x as well. And then lastly, if I look at all the constant terms, so here there's no constant term with a C1 in it, but we do have a minus 2C2 and a minus 4C3. Okay. All right. So we kind of just rearranged everything on the left. Okay. And now that we have it in this form, here there's this idea that for two polynomials to be equal to each other, the coefficients of the powers of x have to agree. So here, this coefficient of x squared on the left has to equal the coefficient of x squared on the right. So that gets us this equation C1 plus 3C2 plus 3C3 is to equal A. Likewise, everything here would have to be equal to B. And finally, this constant term that we have here would have to be equal to the C, okay? Okay. So then we end up with a system of equations similar to how we did with the previous example with matrices. And again, what we would need to do now is we need to check if there is a solution to the system of equations, okay? So to check if a solution exists, we're just going to start trying to solve it. And so the way that we usually solve, again, is just going to be doing elimination. So here, for this system, the augmented matrix we have is 1, 2, 0, 3, 5 minus 2, and 3, 4 minus 4. I guess it would be augmented on the right with ABC. Okay. All right. And let's start trying to reduce it to upper triangular form. So we'll want to eliminate this 2 first. So we can do that by taking row 2 minus 2 of row 1. Okay. So when we do row 2 minus 2 of row 1, we're going to get 5 minus 6 will be negative 1. Here we're going to get 4 minus 6 is negative 2. And here we're going to get B minus 2A. Okay. And if we want to continue to get the upper triangular form, we would need to eliminate this negative 2, which we could do by taking row 3 and if we minus 2 of row 2, that would eliminate the negative 2. Now, when we do this, we'll also get 4 plus 4, yeah, row zeros, right? Mm-hmm. Yes, uh-huh. Yes. Sure. No, that's okay. So let's see here. So, yeah, so when you're reducing it to upper triangular form, so I always do it like one column at a time, okay? So you do want these 3 entries to be zeroed out, but you start with the entries in the first column first, so you don't worry about this one yet, okay? So when we did this operation here, I guess what I'm kind of thinking is I have a 2 that I need to eliminate. So I want to get like a 2 up here so that I can like subtract and cancel it out. So yeah, so I multiplied by 2, and then I'm going to subtract, and that will cancel out that 2, okay? Uh-huh. Mm-hmm. Yeah. Mm-hmm. No, not necessarily, okay? Yeah, but I guess whether you get a row zeros or not will kind of affect what your answer is, and so we'll see that, okay? Yeah, and then just kind of real quick on this one, so we have to get rid of the negative 2. So what I was kind of thinking is if we multiply by negative 2, that becomes a positive 2. Uh-huh. Mm-hmm. Sure. That's a good question, yeah. So once you move on to like, the second column, the problem with using row 1 again to eliminate is that you're going to add or subtract something back into here. You see that? Exactly, right, okay. Yeah, so that's why, yeah, when you move to the second column, you need to move on to like your second pivot then in order to eliminate, okay? Yeah, okay, right, okay, good. So then let's see here. I guess what we have on the right is not super important, but let's work it out real quick. So it's going to be row 3, so C, minus 2, row 2, so just minus 2 times this. Okay. Yeah, so in this problem, we got that row 0, which is a little bit different from what we saw in the last example. So when we focus on like that third row, and let's say we rewrite it as an equation. So as an equation, this would read as like 0C1 plus 0C2 plus 0C3 equals C minus 2 and times B minus 2A, okay? So on the left-hand side, we have 0. And on the right-hand side, in general, this will not be 0. Like it depends on A, B, and C, right? So here, you're not going to have a solution, or at least not for all possible values of A, B, and C. So let's write it like this. So let's say the solution does not exist in for all possible A, B, C. Okay, so what that means then is that means it is not the case that any polynomial is a combination of the 3 that we were given. Okay. And so the conclusion in this example would be that these 3 polynomials do not span our space P2. Okay. Yeah. Mm-hmm. Uh-huh. Okay, yeah. So I guess when we're dealing with problems like this, we're checking if some vectors will span a given vector space. Okay. So span means that every vector in your space must be a combination of the ones that you're given. Okay. So that means when you're trying to, in this example, when we're trying to solve this equation, we need this equation to have a solution for all possible A, B, and C. Okay. Right. So what you're kind of thinking, yeah, what you're kind of thinking is like sometimes this would work out, sometimes that would be okay, but for span, it has to work for like all possible vectors in your space. So that's why here, since it doesn't work for all possible A, B, C, that's why it doesn't span. Okay. So it's sort of a small, like if we were to sort of take a step back and kind of look at how these problems tend to work then. So basically, if you do end up with a row of zeros, so I guess both examples, you kind of start the same way, right? So whatever vector space you're dealing with, in this one, it was 2 by 2 upper triangular matrices. This one, it was polynomials with degree less than or equal to 2. So we were given some vectors in each of the spaces. And we want to check if those vectors span the space. So the first thing that we did in both of the examples is we just created like a combination of the given vectors. Okay. And we set that combination like equal to like an arbitrary element of the space. So you like using variables for that then. When you do that, you should be able to convert it into a system of equations. That's kind of like what happens next. Okay. And then when you start doing your row operations to solve the system, if you don't end up with a row of zeros, so say like in this first one, right? So if you don't end up with a row of zeros, you don't end up with this like 0 equals something possibly non-zero situation. So it means that you're going to have a solution, and that's no matter what A, B, and C are. Okay. So if you don't get any rows of zeros when you're checking for span, that means that they're going to span your space. But then here we kind of see in this example, if you do get a row of zeros, one or more, I guess, then it's not going to span because there won't always be a solution, not for all possible A, B, and C, okay? All right. Okay, so then that's all that I want to say about span for the moment. So I'm going to move on to like another topic now. I'm hoping to talk about null space and column space today. I'm going to start with the null space first. Okay. So let's say that we have a matrix A. Okay. It could be any size, so just like m by n. Okay. All right. So the null space of A. Okay. Which we notate with like n of A, so null space of A. This is defined to be the set of all solutions to the equation AX equals 0. Okay. So then if you're given a matrix and you're trying to find its null space, it's basically amounting to finding the solutions to this equation. Okay. Now let's see here. So if A is size m by n, then the vectors, when you're multiplying by x, x would have to be size like n by 1 in order for the multiplication to work out. Here, it's not super important, but I guess on the right-hand side, it would be like an n by 1 vector there, okay? Okay, so all of the solutions to this equation, yeah. For which one over here? Because I guess we're only thinking about like multiplying the matrix with the vector here then, okay? Because we're only considering like vectors on this side. So then that's why it's a column vector specifically, okay? Okay. So yeah, in this case, so we're dealing with vectors, and these would be vectors in Rn for like a matrix with n columns, okay? So that means the subspace is going to be like a subset of Rn, okay? And it turns out that, in fact, the null space will actually be a subspace. So not just a subset, but actually a subspace. And I think you guys have actually had some questions on your homework assignment related to like the null space of a matrix and proving that it is a subspace. But let me go ahead and just kind of like prove it definitively here as well. So to check if something like a given subset of a vector space is a subspace, so remember that there's two conditions that need to be satisfied. So first, it has to be closed under addition, and second is it has to be closed under scalar multiplication. So we're going to verify that the null space satisfies both of those properties. So I'll start by checking the closure under addition. So the way that closure under addition works is we want to assume that we have two solutions to this equation, and we want to show that their sum will also be a solution. Okay. So here I'm going to start with two vectors, x1 and x2. And I'm assuming that both of them satisfy this equation, so they're both solutions. So when we look at their sum, x1 plus x2, so if I multiply that with matrix A like this, okay, so matrix multiplication is distributive. So we can distribute the A to each of the x's in the parentheses. And then since we're assuming x1 and x2 were solutions to this equation, we know that ax1 and ax2 are both equal to 0. So we have like 0 plus 0 here. So here what we see is that A multiplying the sum will in fact be equal to 0. Okay. So that proves that if we have two solutions, their sum is also a solution to this equation. And that proves that the null space is closed under addition right now. Okay. Okay. To check closure under scalar multiplication, what we'll do is we'll take one of our solutions, x1, and let's say we multiply it by a scalar. Okay. And what we want to show is that this scalar multiple of a solution will also be a solution. Okay. Okay, so here I took a scalar multiple of x1 and I'm just multiplying it with a. So I guess one of the properties of like matrix multiplication is that this scalar c, we can just pull it out to the front. So this is the same as c times a multiplying x1. Okay. So then in that case, again, since x1 was a solution to this equation, so we know that ax1 is 0. So you get like c times 0. Okay. So that means you have 0 is equal to a multiplying cx1. So this shows us that like if you have a solution to this equation, then any scalar multiple will also be a solution. So therefore, it's also going to be closed under scalar multiplication. Okay. Mm-hmm. Ah, that's right. Yeah. Yeah, no need because here since the x1 and x2 are kind of arbitrary. So kind of so when you prove it for like x1, since x1 is arbitrary, it's kind of representative of like any solution. Yeah, that's right. That's right. Yeah. Mm-hmm. All right. Yeah, and then since the null space is closed under addition and scalar multiplication, that means it will be a subspace. Okay. All right. So I want to look at some examples, just like with given matrices, and try and find like their null spaces. So let's start with A being equal to, here I have a matrix 1 minus 1 0, 1 0 2, 1 minus 3, and minus 2. Okay. And I'm just going to be finding the null space for now. Okay. So you guys kind of know how to do this already. But it'll be good to review it because you haven't done it too much so far this semester, I think, but you've done it a little bit. So for nullspace, it's the solutions to ax equals 0. So you just need to solve this equation, okay? So to solve that equation, we could start doing elimination. Now for nullspace, the right-hand side is all zeros. Okay. So you could augment it with zeros here, but since you have zeros on the right, it's just gonna like always be 0. So I tend to just drop the zeros when I'm doing nullspace, and I just add the zeros in at the end after I've like reduced the matrix. Okay. All right, so I'm just gonna take A. I'm gonna start reducing it, and you wanna like at least reduce it to like the usual upper triangular type of form. Okay. Oh, let's see here. So here, I would start by eliminating that -1 in the first column. So I've got my pivot there. So I would just need to add the 1 to the -1 to eliminate it. So we're going to do row 2 plus row 1. Let me see, that will be 0 there. That's 0 plus 1 is 1. -3 plus 1 is -2. Okay. And then maybe if we were to do one more operation to eliminate this 2 now. So we have to use this guy as the new pivot. Okay. So we can maybe do like row 3, and let's see here. I guess I should multiply the 1 by a 2, and then we can subtract. Okay. Let's see here. So we'll get a 0 there. And then just finishing this off. So row 3, see, that's going to be -2, and it's going to be +4. So -2 plus 4 will be +2. Okay. Mm-hmm. No, huh? Sure. Yeah, so the pivots are, I guess, like once, so I guess first it's good to note that your next pivots don't come until you did the elimination in like the previous column. So like right now we just had this one pivot in the first column. We eliminated, and now you've got a new pivot that's in the second column now. Okay. The way that I kind of think about it is like once you eliminate like that, your next pivot will be like the first non-zero entry and like the next like non-zero row. Okay. Okay. All right. And then yeah, so at this point, I guess this third entry is also like a pivot, but we're not really going to be, at least for this example, we're not going to be doing any more elimination. So I guess I would just stop at that point there. Now, if we look at what happens, let's convert this to a system of equations. I'll use x, y, z for the variables. And remember, since we're looking for the null space, the right-hand side is all zeros. Okay. So in this case, we kind of see like z is, oh, sorry, that's 2z equal to 0. Okay. So we get z equals 0. And then if z is 0, y would have to be 0. And then since y and z are both 0, x would have to be 0 as well. Okay. So in this case, there's only one solution, just x, y, z are all 0. So in this case, the null space is kind of trivial, is the word that mathematicians use. But here the null space consists of only the 0 vector, because only the 0 vector satisfies this equation. Okay. And then again, the kind of terminology or the way that people talk about it is they would say the null space is trivial when that's the case. All right. Yes. Just meaning that's like only 0 essentially. Okay. Rather than like something more like substantial. Yeah. Okay. So I wanted to at least do like an example just to kind of show you like that does happen. Probably most of the times in your problems that wouldn't be the case because they probably want you to actually like do something, you know. So let's take a look at like another example. Okay. So here I've got a new matrix. It's a bigger matrix this time. We're gonna do kind of the same thing. So we're gonna try to find the null space. Okay. So we'll do it the same way. We're gonna start row reducing our matrix A. Now our matrix A this time is not a square matrix. So we won't get it into like a sort of like perfectly upper triangular form. Okay. But we'll kind of like get as close as possible, if you will. So I'm going to be doing elimination. I'll do it the same way that we have done in the past. So in the first column, we have our first pivot up here. I'll just eliminate everything in the first column. So to eliminate the 1, we could do row 3 minus row 1. And to eliminate the negative 2, we could do row 4 plus 2 of row 1. Okay? That's right. So I guess in theory, it wouldn't hurt, at least in this first column, to say like use this one to eliminate this negative 2. Technically, you could do that and there wouldn't be any issues. But I think like if possible, I tend to just use the pivot because that's what you want to do in the later columns as well. Okay. So let's do row 3 minus row 1. So minus 3 minus 1. 0 minus 4. 1 plus 3 is what that will be. So that's going to be positive 4. The 5 minus 0 is 5. Okay. And we're also doing row 4 plus 2 row 1. So 2 plus 2 will be 4. Negative 4 plus 8 is positive 4. And 2 minus 6 is negative 4. And then 4 plus 0 will be 4. Okay. So then, now that I've eliminated everything in the first column, so here the next pivot would be this guy over here. So now I'm going to eliminate everything underneath it. So we could do row 3 plus 4 of row 2. We could also do row 4 minus 4 of row 2. That's right. Yeah, pretty much, yes. No, so like maybe a couple things. So let's say this was like a 0 instead, right? Then what you'd want to do is you'd want to swap rows first to get like a non-zero pivot. And then once you swap rows and get your non-zero pivot, then you can start eliminating again. If in the case like everything was a 0 in this second column here, then you'd move on to like the third column to find your pivot then, okay? All right. That's right. Now, when we do this elimination, these should be zeros. These will be zeros, and these will be zeros as well. Okay. And then if I just check what we have remaining, 5 plus 12 here will be 17. And 4, that'll be minus 12 here will be minus 8. Okay. Okay. So then when we go to the third row now, I guess the next non-zero number is actually way over here now. So this is kind of like our next pivot then. Okay. Here, let me just do a little bit real quick. So 17 is kind of not a pretty number, so we could do something like take row 3 and just multiply by 1 over 17 to make it a 1. That would make it nicer. We can also do similar to row 4 real quick. Let's take row 4 and maybe multiply by negative 1/8. Okay. So then if I wanted to kind of finish with the usual elimination procedure, I would maybe just get rid of everything beneath this pivot. So I would maybe do row 4 minus row 3. And that would just give me that row of zeros that we have at the bottom. That's right, yeah. Not necessary just for finding the null space. So just for finding the null space in D, we could have even stopped here. That would have been good enough to start trying to solve it, okay? All right, but I do want to maybe highlight some things at this point. Okay, so here what we did is we did elimination, and so this matrix that we have, it's kind of our like upper triangular matrix at the end, okay? But it's not quite like an actual like upper triangular matrix, partly because it's not even square, right? Okay. So what we ended up with here, this is what they usually call the like row echelon form. To me, row echelon form is just like analogous to like upper triangular form, but let's for like non-square matrices is kind of how I think about it. If I just kind of highlight some of the characteristics of the row echelon form. So you have zeros beneath all of your pivots. Your pivots are also like going to be ordered like down to the right, okay? Mm-hmm. I guess it works for square matrices as well, but it's more general though. Yeah, it's more general. You could say, yeah. So yeah, so the main characteristics is you have zeros beneath all your pivots. Let me just circle all 3 pivots in this Plano form right now. Pivots have to be ordered like down and right, as I was kind of saying. All rows of zeros need to be at the very bottom of the matrix. So if you had like a row of zeros further up, you would need to maybe do a row swap perhaps to make sure they're all at the bottom. The last thing is, and I don't think everyone requires this, but I know some people do require this. So sometimes for the row echelon form, the pivots are required to be equal to 1. which is what we have in this example. So if you had like a pivot that was not equal to 1, you would maybe need to do a row operation like this to make the pivot a 1, and then it could be in row echelon form after you've done all of that, okay? Okay. So let's take a look at what's going to happen now that we've reduced it to row echelon form. Okay, so here, let me run it like the system of equations that we end up with. So the first row gives us an equation. It's going to read something like a 1x1 plus 1x2 plus 4x3 minus 3x4 plus 0x5. And for the null space, the right-hand side is always 0. Okay. The second row gives us x2 plus x3 minus x4 plus 3x5. And then we have equals 0 again. The third row gets us just 1x5 is equal to 0. Okay. So here we have kind of like 3 equations that we ended up with. So because we had 3 equations, we'll only be able to solve for like 3 of the variables that we have. So then the remaining 2 variables that we're not going to solve for, those are going to be our so-called free variables, okay? Okay. Okay. Now there is some freedom to decide like which of your variables will be your free variables and which ones are you going to solve for, but there's kind of a convention that is useful to follow, especially, I guess, in this class, okay? So what we're going to do is we're going to refer to our like reduced matrix over here, and the variables that correspond to the pivot columns. So in this case, that will refer to like x1, x2, and then like x5, okay? Those would be the variables that we solve for. So I guess I'll refer to them as like the pivot variables. Okay. So in this example, that's x1, 2, and 5. So then the other variables, so the variables that correspond to the columns without pivots, in this case, columns 3 and 4, so x3 and x4, those would be the free variables. I'll just maybe write it like that. Yeah, so there's sort of a correspondence then between like not having a pivot and being a free variable. Okay. All right, and then people will do this in slightly different ways, but the way that I tend to do it myself is so we have two free variables, x3 and 4 in this case. So what I tend to do is I assign a parameter to each of the free variables. A parameter just referring to like another variable, basically. So I use like S and T for x3 and x4, but you can use like any 2 letters that you want. So I know a lot of people would do like A and B. A lot of people like R and S actually, but it doesn't matter. So the idea is since these are free variables, they can take on any value. And because they can take on any value, that's why we're just going to assign them like a variable value. Okay. Okay, now looking at the rest of our system of equations now, we have x5 is equal to 0. Okay. And then I want to solve for x2. So what we're going to do is we're going to do sort of the usual back substitution. So we're going to plug these three into here now, and we can solve for x2. So if we plug these in for x3, 4, and 5, and then kind of move everything over, x2 is going to be minus s plus t, and I guess x5 is 0, so it's just going to be that. Okay. And then likewise, we need to back substitute all this into the first equation to solve for x1. Maybe I'll write that one out a little over here. So x1, when we do plus x2, it's minus s plus t, plus 4 x3, 4s, minus 3 x4 is t. Okay. So let me see, that's a 3s minus 2t, but then we have to move it over. So x1 would be minus 3s and plus 2t. Okay. All right, so now I'm gonna, so we found the solutions that s and t can be like any real number. Okay, so there's infinitely many solutions. What I tend to do is I tend to write the solution in a certain form. So I'm gonna kind of write everything in terms of vectors. So I'm gonna put x1 through x5 as like a single vector x. Okay. And then I want to like kind of take the right-hand side and also write it in terms of vectors. Now I'm going to write it in a certain way though. So I'm going to write it as a linear combination. Okay. Now there's kind of two ways that you can do this. So if you read off the coefficients of s, here it's -3, -1, 1, 0, 0. And then if we read off the coefficients of t, it's 2, 1, 0, 1, 0. Okay. You can also kind of, instead of like doing it in terms of like the columns, you can also think in terms of the rows. Like x1 is going to be -3s plus 2t. x2 is going to be minus s plus t. So whether you do it in terms of columns or rows, it's up to you. I think columns just seems easier to me. And then again, s and t can be any real number, so you can maybe like leave a comment like that as well, just to represent s and t can be any real number. And then this is going to be like the null space for this example. Okay, so here then the null space is not trivial this time, okay? But we see that the null space consists of all the linear combinations of these two vectors. Okay. Now, because here we see the null space is all linear combinations of these two vectors, you could say that the null space is the span of these two vectors. And so I know sometimes people might write it like this. I don't think it really matters how you write it. Okay. I guess those would both kind of be acceptable for like what is the null space of this matrix. Okay. All right. Now, I want to touch on, so we talked about row echelon form just now. I also want to touch on the reduced row echelon form as well. Okay. Okay, I just need to pick one. Okay, so the reduced row echelon form, it's similar to the row echelon form that we have up here. There's just like, I guess it's one extra requirement for your matrix to be in the reduced row echelon form. So in addition to satisfying these conditions for the row echelon form, to be in reduced row echelon form, you also need zeros above all of the pivots as well. Okay. So let me take the matrix that we had over here that we ended up with, and I'm just gonna do a little bit more work to put it into the reduced row echelon form. Okay. Now let's see in this problem here. So let me just identify the pivots again. So these were the 3 pivots. Okay. So if we did want to put the matrix into reduced row echelon form, we're basically going to do a few more row operations. So I need zeros above the pivot, so I need to eliminate this one up here. So to eliminate this one, we would use this pivot here in the second column. We could maybe do row 1 minus row 2 for now. So that would eliminate the 1, which is good. We would also get 4 minus 1 is 3 up there. Here we're going to get negative 3 plus 1, be negative 2. Okay. And then lastly is we need to eliminate this 3 over here because it's above one of our pivots. Okay. So to get rid of this 3, we could do like row 2 minus 3, row 3 in that case. Okay. Now when we do this operation, because of all the zeros here, it's not going to affect any of these entries. So in particular, it's not going to ruin like our second column. Oops. And then here we had the 3 minus 3, which gives us the 0. Okay. All right. And then this would be the reduced row echelon form of A. Okay. So I guess I'll maybe mention a couple of things. So the reduced row echelon form, it's like a little bit more simplified compared to the like non-reduced row echelon form. Okay. I guess one property is that the reduced row echelon form of a matrix is unique, meaning every matrix will have like only one reduced row echelon form. But in contrast, the like regular row echelon form is not unique. So every matrix can have like more than one possible row echelon form, but the reduced row echelon form is unique. Okay. Yeah, that's right. So I just maybe if we were to look at like what would happen if we try to work through the last example again, but just using this reduced row echelon form as opposed to like the regular row echelon form that we did, okay? There's not that much difference, so when you're just finding the null space, it doesn't really matter. If you're trying to, if you reduce it to row echelon form or reduce row echelon form, okay? The only difference really is if we were to like write out the system of equations, okay? And let's say we do like the same thing that we did, sort of, where we'll choose x3 and x4 to be free because they have no pivots. We had x5 is 0 still, so that's good that we get the same thing. This time when you're solving for x1 and x2, it's just like a little bit easier to solve for them. Because here we just need to move the x3s and x4s over. Whereas if we go back to up here, there was this one thing where when we were solving for x1, we had to like back substitute for the x2. Okay. And so like some of the back substitution will be like, or how would I say it? You won't have to do as much back substitution if you reduce your matrix to the reduced row echelon form, okay? So it's kind of a trade-off. You have to do more row operations, but you'll do a little bit less back substitution when you go to reduced row echelon form. Okay. I'm about out of time, so that always happens. I was hoping to touch on the column space as well, but I wasn't able to get to that. But let me kind of say just one more thing to end the review. So let me just kind of quickly write down. I'm going to copy the matrix A again real quick. I'll do it over here. Uh-huh. Mm-hmm. In order to get it to the reduced row echelon form. That's right, yeah. Mm-hmm. So it's kind of a trade-off, what you prefer. Yeah. Now, in some types of problems, though, the reduced row echelon form is more useful. Okay. So like for just finding the null space, it doesn't really make a difference. But I want to kind of show you, like, or show everyone some of the like information that you can glean from the reduced row echelon form. Okay. So in this case, our sort of pivot columns were columns like 1, 2, and 5, right? And then like columns 3 and 4 were like the non-pivot columns, or like the free columns, maybe, if you want to call it that, because of the free variables there. So the reduced row echelon form gives us some information about how the columns of A are related to each other. Okay. So because columns 1, 2, and 5 were the pivot columns, okay, that means that columns 1, 2, and 5 in the original matrix A are like linearly independent. Okay. Yeah, so columns 1, 2, and 5, that basically the pivot columns, are going to be linearly independent. Right. Yeah, independent. As for like the non-pivot columns, so they happen to be linear combinations of the pivot columns. So specifically, the third column that we have in A, okay? So notice in the reducible echelon form, in the third column, we have like 3, 1, 0, 0. Okay. So what these numbers are telling us actually is that the so from the third column of the reducible echelon form, if I take 3, okay, times like the first column of A, and I'm going to take 1 of the second column as well. Okay. Notice that this is going to add up to be the third column of A. Okay. Yeah, I'm just looking at the third column of the reducible echelon form. Okay. So yeah, right. So I'm kind of taking like 3 of the first column plus 1 of the second, but from the original. Okay. That's right, yeah. And so here specifically, you can get like the exact like linear combination, if you will, from the reducible echelon form. So similarly, the fourth column, if you look at the like reducible echelon form of A, so if you take like -2 of the first and like -1 of the second, but from the original matrix, that should equal like the fourth column and the original matrix as well, okay? Yeah, so this kind of information you don't get from like the regular row echelon form, but you can get it from the reduced row echelon form. Right, okay. So I think you have some problems that are kind of like, find your pivot columns and then also like express the non-pivot columns as a linear combination of the pivot columns. So for those types of questions, you can answer it by reducing all the way to the reduced row echelon form, okay? All right. So I guess I'll go ahead and end the review at this point then. It's a little bit over time, but that's okay. And so now I'll have to talk about column space next time instead. All right.